So today, we're diving into some really fascinating research that puts forward a whole new mathematical structure. It's called the Perez Hourglass, and the claim here is that this isn't just some pretty pattern, but it might actually be a blueprint for the future of technology itself. Let's dig in and see what makes it tick. And it all kicks off with a question that honestly sounds like it's straight out of science fiction. What if a fundamental secret to quantum computing, to unbreakable codes, even to a new kind of AI, was hiding inside a pattern that most of us probably saw once in math class and then totally forgot about? So it all starts with something you probably remember, Pascal's triangle. You know this one, right? You start with a 1 up top, and every number below is just the sum of the two numbers right above it. It's simple, it's elegant, and it's a world built entirely on addition. But here is where it gets really interesting. The research paper says this triangle has a hidden twin, kind of an antimatter reflection of itself. This southern half isn't built on adding the numbers above, but on this unique rule of subtraction. It's like a mirror world, and trust me, it changes the whole game. And when you stick them together, you get this, the Perez Hourglass. Now, according to the author, this isn't just something neat to look at. The claim is that this structure is packed with profound rules, a deep logic that could literally be the architecture for a whole new wave of technology. So what is it that makes this shape so special? Well, the paper lays out what it calls the 7 fundamental principles. I kind of like to think of them as the 7 wonders of the hourglass. These are the hidden rules that apparently give this thing its incredible power. We're not going to go through all 7, but just to give you a taste, we're talking about some really amazing properties here. Things like a mirrored version of the Fibonacci sequence just popping out of the numbers, a perfect balance where the rows add up to these simple, constant numbers, and a super deep connection to fractal geometry. Okay, so one of the first mind-blowing things is how the Fibonacci sequence, 1, 1, 2, 3, 5, 8, that pattern you see everywhere in nature, it just naturally appears when you add up the diagonals of that antimatter half. That's a huge clue that this structure is plugged into something really fundamental. All right, get this for another bizarre property. If you take any row in the entire infinite bottom half of this thing and you add up all the numbers, the sum every single time is exactly positive 2. It doesn't matter how long the row is or how crazy the numbers get, the sum is always 2. And the flip side to that is even cooler. If you just ignore the ones on the very edges and only add up the numbers on the inside of any row, the result is always a perfectly balanced 0, a constant state of equilibrium just hiding in plain sight. And the last wonder we'll check out is this. If you basically throw out the numbers themselves and just look at whether they're odd or even, bam, you get this image. The iconic Sierpinski triangle fractal. This shows a self-repeating pattern that goes on forever, connecting the hourglass to the world of chaos theory. It's beautiful. But out of all these incredible rules, there's one that the paper says is the most important of all. It's called Theorem 7, and they refer to it as the golden key, the one principle that supposedly unlocks all the practical, world-changing stuff. The idea behind this theorem is actually pretty simple to picture. Just imagine you could fold the entire hourglass right at its skinniest point, like a piece of paper. When you do that, every number from the top half lines up perfectly with a number from the bottom half, making a pair. Theorem 7 is all about the secret relationship between these pairs. So here's the crucial part. Theorem 7 claims 2 things are always true. First, the numbers in a pair always have the same parity. An odd number always faces an odd number. Even always faces even. But second, and this is the real kicker, each pair of values is globally unique. That pair of numbers, say a 6-2, will never ever show up again anywhere else in the entire infinite hourglass. It's like a unique fingerprint for every single position. And this quote from the paper just nails why this is so important. It says, Theorem 7 is what turns the hourglass from just an interesting pattern into a deterministic computational substrate. In other words, it's what makes it a reliable, predictable framework you can actually build things with. So if Theorem 7 is the key, what doors does it actually unlock? Well, the paper then goes on to propose some seriously game-changing applications that could be built on this foundation of guaranteed uniqueness. The first big one is in quantum computing.
The paper suggests the hourglass provides this natural, stable grid for arranging qubits. The idea is that its fractal geometry creates a kind of self-correcting system where errors are naturally pushed away, leading to a much more stable and reliable quantum computer.
That global uniqueness property, it's also unbelievably powerful for cryptography. The paper claims you could use it to generate an endless, non-repeating string of numbers, which is the holy grail for a truly unbreakable encryption method. It also suggests new ways to keep our communications safe from future quantum computers. And this might be the most ambitious claim of all. It's in AI. The paper introduces something called the Perez Hourglass Associative Memory, or PHAM. It's a design for a new kind of computer memory that acts more like a human brain. But the author claims it would be the first perfect version with infinite capacity and zero errors. And this table from the research really puts that into perspective. It compares PAM to what we have now, things like hot field networks. You can see our current systems, they have limits. They're always going to have data collisions. But PAM, the claim is it's literally infinite, with zero collisions, and it's supposedly way better at handling noisy or incomplete information. So to wrap up, the paper takes a step back and asks a bigger question. It suggests that this structure isn't just some clever human invention, but maybe, just maybe, it's a fundamental pattern that connects huge areas of math and maybe even nature itself. And in one final, fascinating twist, the paper connects the hourglass to the work of Srinivasa Ramanujan, one of the most brilliant and mysterious mathematicians in history. It suggests this hourglass might be the first real geometric picture of his Mach theta functions, a puzzle that has stumped mathematicians for over 100 years. And this all builds to the author's final, really powerful line. It completely reframes how we should see this thing. It's not just a passive object. It's an active, computational machine. The sand is no longer falling. It is computing. And that leaves us with this final, kind of mind-bending question that this whole paper inspires. When you see these deep connections to Pascal, to Fibonacci, to Ramanujan, all tied together by the golden ratio, you just have to wonder, is this just a beautiful mathematical coincidence? Or could the universe's own operating system be written in a language we're only now beginning to understand?